So, nice to meet you. My name is Armony. I'm an electrical engineer, and I work at NSLComm as a system engineer. And first of all, you can see that there's NSLComm and Beetlesat, so if you stay focused by the end of the presentation, you'll know the difference. But we're here to talk about our new satellite that we launched earlier in this month. The guys before me presented few important principles in the new space and nanosatellites. So we implemented most of them, and in the upcoming few weeks, we're going to demonstrate those capabilities from space. So meet NSLComm, our new communication satellite. 3 years of hard work brought us to this moment. This was at the beginning of the month at Space Canaveral, US. By the end of the presentation, we have the video, but this is the moment where the clock says 0, that the rocket was fired. And 1 hour later, our satellite was separated from the rocket. This is SpaceX stage 2. And in the red circle, it's hard to see, but this is the moment where our satellite was born and start its own separated way in space. So before I dive down and explain about the practical satellite and makes you familiar with our satellite, let's discuss a bit about the orbit and in zoom out. So the traditional communication industry from space was geosatellites. Satellites that are located very far from Earth, 36,000 kilometers, which is far away, and you need a very strong transmitters and in order to transmit into that satellite. And the new age of small and small satellites for communication are much closer to Earth. For our example, our satellite is about 550 kilometers from Earth. And it makes sense. If it's closer, you need less energy to transmit to it, and you can receive and transmit for much lower instruments on ground. One sentence about the orbit. So in a geostationary orbit, the satellite is relatively at the same position to the ground. You don't need to gimbal your antenna, and you look at a specific direction at space, and the satellite is always going to be there, because one orbit of the satellite equals 1 orbit of the Earth, so it spins with us together. LEO satellites spins much faster since they're in much closer orbit, and they finish 1 orbit of Earth in 90 minutes. 90 minutes said that we have around 15 passes per day, which means because of the polar orbit of the satellites, from each ground station, each location on Earth, you can see the satellites between 3 to 4 times a day, which brings us to a global coverage of Earth. So this is our satellite that was launched. This is how it looks like. This is an illustration. This is the real satellite in our lab. It's a nanosatellite. It's a 6U satellite. If you're not familiar, 1U is a cube of 10 centimeters by 10 centimeters by 10 centimeters. So 6U's, you pack 6 of them together. It's like a shoebox, and everything is packed inside, besides the deployable antenna, which I'll get to it soon. I know you're curious about it. So inside this small package, we have everything you need for a satellite. There's the altitude determination control system, which includes reaction wheels, magnetometers, multiple sensors from each kind to determine the orientation, and also a GPS receiver. We communicate with it using a VHF UHF antennas, and of course it includes solar panels and batteries. All of this in a small package. And inside of this package, this is our payload, the state of the art. It's only 2.5U payload, this big. It has inside a small volume to throughput radar SDR modem, which means we can configure and update the software and the firmware. It has a programmable logic inside, so we can change versions, update softwares, and load new waveforms for transmission into it. The main mission of the satellite, as will be described soon, is store and forward. That means that when it passes over ground location, you can send a message to it, message or a file, and when it gets to another position, it can transmit it down like a mailman. It stores forward. We're doing this using a Ka band, which is very high throughput. It's not the capacity you are familiar with from IoT devices. It's much faster. We'll get to it soon. And also we have a secondary mission, which is S-band. It's another antenna of the satellite that can transmit, this time, IoT protocol for different purposes. And if it's not enough in such a small package, we also host a small card by Ramon Space that we check for them in orbit. And in order to check our payload and the deployable antenna that you'll see in a second, we have a set of 3 cameras on board. 2 of them are for photogrammetry process, which means that we take I'll go back to the antenna, it will be much clearer. When the antenna deploys, and this is a deployable antenna, which we'll get soon, when the antenna deploys, we want to know that it was deployed perfectly or as close as to perfect. So we need to make this assessment process. On the surface of the antenna, there are many small dots that we can take picture from 2 different angles with 2 cameras and do this process called photogrammetry. And then we can create a 3D model of the antenna and know what's the performance of the antenna if it was deployable right. So the antenna is the main is the gimmick of the satellite, or the main cool part, which is deployable. Right here in the pictures, you can see a test that we did in a zero gravity plane. Here in the red circle, this is the antenna when it's folded. When we launch the satellite, the antenna is folded on top of the satellite, and then we fire some sort of mechanism, and the antenna deploys, and it deploys by itself. That means that the antenna is built from a special material that remembers its shape, and in a zero gravity environment, it just pop up to the same shape that it's familiar with. So this is our patent, and it's built in our lab, and it's very complicated process of folding it right and testing it right. And here you can see the deployable antenna where it's still folded, and this is a 0G. It's hard to see, but here it says almost 0G at the same position. They pull the string that was attaching it, that was holding it, and it just pop up to the same position and the same shape it was familiar with. But you can think of why we should put so much effort in create a special antenna that was folded and not just put a full antenna that's already open on the satellite. So as the guys before me said, although launches from space are much cheaper these days, it's still expensive to send something which is heavy or big to space. This is why if we get to make the antenna smaller, we can make the satellite smaller. We can put it on a smaller rocket, or we take less space on the same rocket. And then is how we make our service of communication from space much cheaper. So let's talk about the mission, because this is what we're dealing these days in our company, and this is what makes the business. So as I said, it's a store and forward satellite. And let's say, for example, the satellite is here. We need 1 or more gateways. And in the gate, we have a modem by Ayecka, which helps us on the ground segment. And on the other side, we have 1 or many, hopefully many terminals spread around in far fields areas. And as I said before, when the satellite goes over the ground, the gateway, it takes files from one side. It can transmit them to the ground terminals, and vice versa. It can collect a lot of data from many user terminals and pull all of the data to the gateway station. The rates are quite amazing. We can transmit up to 2 gigabits per second from the satellite to the gateway. If the satellite collects data from many satellites, we can drop them in one pass to the gateway. And the TX rate from each terminal to the satellite can reach up to 50 megabits per second. And this is very nice, but what's next? So these days, we're handling the IoT, not the Internet of Things, but the in-orbit testing of NSLSat 2. But we're already looking forward for our next big project, which is Beetlesat. I promised you the explanation. So Beetlesat is the name of our new constellation project, and this is the rebranding of our satellite. This is how it's going to look like. Beetlesat will contain more than 200 satellites. It's going to have inter-satellite link using the same deployable antenna that you saw before. It's going to have secure point-to-point connectivity, not only for IoT devices, but mainly for high throughput usage. And the main thing is that we're going to deliver low latency, lower than the terrestrial networks. Now we have few videos for you. The first one is from the liftoff from the launch at the beginning of the month. This was filmed in Cape Canaveral by our team that was over there. And this is liftoff. We launched into space using SpaceX's Falcon 9 Transporter 6, which also landed after this. But I can tell you that I couldn't care less if it lands or not. I could care only about the satellite at those moments. It landed. I don't know if we can see it here. Let's see. No, not in this video. Another nice video is the separation moment. If you can listen carefully, it says NSLComm 2 confirmed. I'll play it again. Look. It's a bit hard to see, but if you're on the video, so text me later. And I'll finish with our demonstration video of Beetlesat, which is our next big project. Before I'll start it and we'll finish with that, I just want to say that the space industry is something that you learn from each generation to the next. So a lot of things that we learned from NSLSat 1, we improved in NSLSat 2, and a lot of NSLSat 2 technology is going to be in Beetlesat constellation. So the idea is to send many satellites into many orbits. Each orbit is a circle of satellites following each other. Between each neighbor satellites, we're going to have inter-satellite link, which means each satellite always sees the one in front of him, in the back of him, and its two sides. This is when it starts its life. Deploy solar panels, deploy the inter-satellite link antennas, which you just saw before. We also have beams that transmit to the users forwarding Earth. Everything is gimbaled, everything is configured. And in few predetermined orbits, we can create a network constellation that provides real-time data between any point to point. So if in NSLSat we have one gateway, here we'll need many gateways, much powerful with more antennas. And this is some of the use cases. First of all is cellular backhauling. Also for aviation, we can track airplanes and give the access of internet to those passengers. Also maritime. And each beam that the satellite is looking for doesn't have to be a single point. It can be many points located together. It's co-located terminals that transmit together, and we can split the channels between them. Of course, there is the Internet of Things solutions. It's worldwide, so we can cover remote areas. And hopefully, by the next time I will stand here, so I can demonstrate Beetlesat live. So thanks.